So in today's Q&A session, we'll do a bit of a rehearsal of the lectures 9 and 10 from previous week, as usual. So in these lectures, we talked about memory management on different levels. So we talked about memory allocation policies, strategies, and the general problem definition of memory allocation. So why do we have to do it? We took a quick look at static memory allocation and then figured out dynamic memory allocation is the way to go. And for dynamic memory allocation, we had to look at placement strategies and the result of placement strategies, which is fragmentation. So unused pieces of memory that, just are the result of partitioning our memory into pieces of certain sizes. And then we took a look at how to enable memory mapping and protection using two different approaches. So we took a look at segmentation and we contrasted this with paging. And since we have paging, we can enable a functionality called virtual memory, which is available in most non-embedded computer systems today. So we took a look at demand paging. We took a look at which strategies exist to replace pages in case we run out of physical memory. Then we took a look at problems that may exist due to being able to page out pages of memory to secondary storage, which is called thrashing. And we took a look at the working set model to figure out what the reasons for thrashing are and how we could maybe reduce thrashing. So memory allocation policies, strategies, and the problem definition. So what we figured out is that we needed a number of different policies. We needed policies for placement. So if there is a memory allocation from an application, then placement is the policy that decides which area of memory should be allocated to this request. We have a policy for fetch. So the fetch policy tells us when we should actually swap in memory contents. So we can do it when it's required. We can do it in advance, for example, if we do some look ahead. And we took a look at replacement policies. So replacement policies tell us, like, if we run out of memory, for which part of the memory, page of the memory, does it make most sense to be swapped out? So which is maybe the most efficient approach for replacing pages in memory. And the first thing we took a look at here in closer is the memory allocation problem. So the memory allocation problem is the problem to solve, to find an allocation of memory that satisfies a number of requirements. And these requirements can come from user processes. So we need memory for code, for static data, and for dynamic data, which can be stored on the stack and on the heap. So local variables on the stack, malloc allocations on the heap. And also the operating system needs memory for its own operation, of course, also for its own code and data and stack and heap, but also for central data structures here, process control blocks, data buffers for input, output, and so on. So we figured out that we definitely need methods to do memory allocation because we cannot just allow any application to request whatever section of memory it wants if we want to enable multi-programming on our system. So if we want to have an application coexisting with another application in memory at the same time, and all applications coexisting with the operating system in one memory. So the first algorithms we took a look at were concerned with how we do memory allocation. So the most simple way is just to do a static memory allocation. So in a static allocation, actually, I do some pre-calculation. I maybe know how much memory each application needs. And this enables me to just use fixed memory areas for the operating system and the user processes. This is especially useful if I know all my processes in advance and their memory requirements, and maybe I can compile them all together in one large binary. This is still often done for very small applications for microcontrollers where actually nothing changes. So in an embedded control unit for a car, you won't want to download any additional code at runtime. So the embedded controller has a fixed set of tasks, which are, as we see later on, also fixed in a static schedule maybe, and which do not do any dynamic memory allocations at runtime. So we know the memory allocation. We can do static assignment of memory to each of the applications on our computer. Now, the problem with static allocation is that this limits our degree of multi-programming. So we cannot just start an additional application, which also needs memory if the memory has already been allocated to the existing applications before and there's no free memory left. We might need, limit other resources like I/O bandwidths. Like if we have too little memory available for storing I/O data, so-called buffers, then even if our devices are fast, if we can't just store the data somewhere, then we'd probably have to throw away data because we ran out of buffer memory. So static allocations might lead to limitations of these I/O resources. And unused operating systems memory cannot be used by applications. So if we do an over-allocation of the memory that the operating system requires, well, then applications cannot make use of it. So what we want to do is we want to perform a dynamic allocation, and we've seen that for dynamic allocation, we need to figure out which parts of our memory are actually free. So we usually split up our memory in sections of the same size, because we can't do it byte by byte, because otherwise the administration overhead would be far too high. So for each of these sections, we can store information if this section of memory is free or occupied. And we've seen a simple way to do it using bitmaps as free list management approach. So each bit indicates for one of these sections of our memory if this section is used or not in use. And when there is a memory allocation that comes in, then it's easy to iterate over the bitmap to find unused sections of memory, and then we can allocate them. We've seen that dynamic allocation can also use linked lists or linked lists in free memory. And we've seen that releasing memory is actually the more complex problem here, because when you allocate memory, your first task, when you don't want to move memory around, which you usually try to avoid, your first task is just to find a block that's big enough. We've seen approaches for this. But when you release memory, you might release a block of memory that's adjacent to one or two free blocks to the left or right. So at lower or higher addresses directly adjacent to the memory range you're releasing. And so it makes sense to merge these adjacent free gaps again. If you merge them again, you obtain a larger free area, and this can then satisfy larger allocations, obviously. So we've seen different approaches for placement strategy, and the algorithms we've seen were first very simple. So we've seen the first fit approach. So we go through our list of free memory areas here, and we have an allocation of size n. So we just choose the first one where a block of size n fits in. We split this one into a block of size n, which then gets allocated, and the rest from n+1 to the end of that free block, if there's more space in that free block than the allocation. And we have a smaller new free block, and we have an allocation. So first fit always starts from the start of memory. That might be a bit problematic because then things tend to pile up at the start. Next fit actually remembers where the last allocation has took place. So next fit actually just continues looking for the next free memory section of appropriate size from the last point it left off. So it always goes around in memory, and when it reaches the end, it starts from scratch. We've seen the best fit approach, so we find a range of memory where our block ideally fits in exactly. We've also seen worst fit, and then we've seen a more advanced method, so-called buddy method. And the buddy method actually is based on the idea of splitting our memory into areas of a size which is a power of 2, and then we can allocate something. So if we have, like shown in the picture here, a memory of 1024 units, then we can, for example, in our first step, allocate 70 units. 70 units, we need to figure out the next largest power of 2, which is 128. So we split our 1024 into the largest power of 2 sections which are available. So the right half will be 512, and then we need to split the left half a bit further, which leads us with an allocation for A. and 2 free blocks of 128 and 256 memory elements in size. And then we can see we can split this further down. So we in the next allocation for 35, for B, we could split the first 128 block down into 64 blocks and allocate it to B, and so on and so forth. Now this works pretty well, but as we are restricted to powers of 2 in memory size here, to make this administration very simple and very easy to do, we see an effect called fragmentation. So fragmentation means that if we allocate 70 memory elements into a section that's 128 of size, then obviously we have 58 unused elements, and we cannot reallocate them further now. So allocations can create memory fragments inside of the allocated memory area. That's the problem further down, the internal fragmentation. But we can also cause external fragmentation by creating free elements in between some other allocated elements, like the 64 element for allocation 80 in line 3 of the diagram here. And these also won't be available here. And external fragmentation is especially a problem with all of the list-based strategies, so first fit or best fit. We've discussed quite a number of more details about this, so this is just giving a quick overview, obviously. Then we took a look at the approach of how to split our memory into in a bit more intelligent way, let's say. So we've looked at 2 approaches. So the top left approach here is segmentation. So in segmentation, you define, well, what we call a segment. A segment is just a base address and a size of a memory region here. So we use these segments to actually map addresses from a logical address. So for example, we split our logical address here in the top right half under the segmentation text here into 2 parts. So the left 2 digits, for example, give the number of the segment, and the right 6 digits gives the offset of our whatever address inside of that section. And this 02 is then actually mapped with the address, base address of the segment table to give an index into the segment table. And this information then gives us a base address in physical memory. We figure out this base address and add it to the offset inside of that segment. And we also figure out if, for example, we have a limit here. So 4FFF is our limit. If the offset is actually less than our limit, so a segment essentially guarantees that an excess, given a certain segment number, only is available inside of the limits of the segment. So inside of the first hexadecimal 5000 bytes here, or 500 memory addresses here. And if this exceeds the address, well, then we get a trap, an access violation. So this is simple, and this is something that was done by the very first Intel processors, the 8088, so not the absolutely first Intel processors, the first 16-bit ones. And segmentation is actually available as a memory allocation technique also in most modern x86 processors, but it's not that nice to use because segments can be a bit unwieldy to handle. So another approach is shown on the bottom right-hand side, which is paging. So in paging, we don't use segments of arbitrary size, but in paging, we split our memory into sections of exactly the same size, for example, 4 kilobytes. And for each of these 4 kilobyte segments, I can define what we call a mapping. So for each of these 4 kilobyte segments, I can have an entry in the page table. And this entry in the page table actually tells me where in physical memory a page with a certain so-called virtual page number can be found. So what's done here is that the logical address, so the address generated by your program, which is output by the CPU to the so-called memory management unit, this logical address is split in 2 parts. The left-hand part is the virtual address, which gives the index into a page table. The right-hand part is the offset inside of a page. So for example, for 4 kilobyte pages, 4 kilobytes are 4096 bytes, so 2 to the power of 12. The offset part is always 12 bits, and for example, on a 32-bit machine, the virtual address part would be 20 bits large. So the left-hand 20 bits are then used as an offset into what we call a page table. And this page table consists of information about the physical address where we can find this page in physical memory. And it also has additional information not shown here, especially access information. So for example, we can distinguish on most processors between a read access, a write access, and an access to fetch instructions, which is called an execute access. So like with Unix files, we have protections for pages here, RWX, and maybe a couple more, which indicate like, is this access permitted? Like if we try to write to a page for which we only have read access, we would also get an access exception, and our program would probably be terminated, and we get this infamous segmentation fault, which you've probably seen before. So this is, especially the page table here, is quite simplified. If we used 32-bit addresses with 4 kilobyte pages, we'd have 20 bits of virtual address. This means we have 2 to the 20 number of entries, so around a million entries in our page table. Each would be at least 4 bytes because it gives us the start address in physical memory. So essentially, this would mean we would waste 4 megabytes of RAM for page tables alone if we wanted to map each page on a 32-bit machine. Now imagine how you would do it on a 64-bit machine. You'd probably run out of memory after storing your page tables and would not have any memory left for your actual program. That would be a bit of a shame, right? So usually page tables are structured a bit more complex in a tree structure. So you have a root page table, and this then contains only links to populated page tables on the 2nd, 3rd, and sometimes even the 4th level. So if we have demand paging available, then we can actually also indicate if a virtual address actually currently has a representation in physical memory. So that means if data or instructions we are trying to access, if this is actually in memory, in physical memory, in RAM right now or not. Now, if it's not in RAM, what's going to happen? We need to move it into RAM. Why can this happen? Now, the idea is that many programs want to share the physical memory, and usually there's something we call an 80-20 rule. So 80% of the code uses only 20% of the available main memory. So essentially, if we would do the full allocation for all processes at the same time, we'll constrain ourselves. And the idea that was introduced is to create and provide something we call a swap space on background storage, so usually a disk. And this swap space can be used to put the contents of pages which are not currently used out to disk. And if we need them later, we would mark the virtual addresses for which we just moved the physical data out to disk. We would mark it as unavailable. So whenever there's a future access, like we are jumping into code on that page, we are reading or writing data on that page, then we get an exception, which is called a page fault here. And this page fault then leads to actually figuring out, do we have some information on the background storage here, as shown, for example, for a page frame with contents F here. And then we need to look for a free page in memory, or we need to create a free page in memory. And if this page is free, then we can copy data from the disk back into main memory, change the page table entry for this memory location, or for this memory page actually, to be available at the physical location where we just loaded it to. And then we can actually retry this instruction. So this load has generated an exception. And so whenever this data is now finally available, we have to rerun this load. And depending on the CPU, this is done automatically. On some CPUs, you actually have to correct the program counter by hand. Now, this is going into too many details for the operating systems course here. That would definitely be part of an advanced operating systems course. So paging is a very nice method if you have applications that behave like using only a small part of the memory for most of the time. So for example, you could imagine having a word processor, and you might need code to display text, to do spell checking, to format stuff all the time, but you only print very rarely. So all the code related to printing in your word processor Does not have to be loaded into memory all of the time. You just need to load it when you actually want to print something, and you can kick it out again when your printing is done, obviously. So for applications like these, this can be very useful. So the problem is when we want to swap in a page from external storage, well, what happens if there is no free page available? Well, then we have a problem, obviously. So, and the solution for this problem is we have to make a page available. So the sequence of events here is that first we get a page fault, then we have to select a page which we want to free because we think it's not recently used, for example. We move it out to secondary storage, thereby creating a free page in RAM. And then we can page in the requested page that has caused the page fault, and then we can repeat the memory access. And the problem here is to decide which page to choose to be paged out. And this is usually called the victim. So this is just kicked out of memory and moved to secondary storage. And we've seen a number of replacement strategies. So we've seen first in, first out. So we just keep a timestamp here and we look at the page that's still in memory that has the earliest timestamp, and we kick it out and load our new page into that location and update its timer, obviously. We've seen an optimal replacement strategy that uses the time until the next access to the respective page. So if we knew how much time in the future would pass until this page is needed, then we could use this optimal strategy. Now, unfortunately, we don't have a crystal ball, so we can't look into the future. So optimal is only a very theoretical approach, which would be nice if we had this information, but usually memory allocations are unpredictable, so we cannot really tell which would be the optimal strategy here. So we're trying to approach something like optimal strategies, and one way to do this was least recently used, so LRU. So here we check which of the pages has been least recently used, so which actually is not the oldest in memory, as with first in, first out, but we actually store access times. So we check which of the pages actually has not been used for the longest time, and we just extrapolate from this, like if this page has not been used for whatever 2 minutes, then well, the probability is very low that it will be used soon after, so we just kick that one out here. And pages which are used very frequently, these get their counters updated, their timestamps, and so they're not endangered of being kicked out relatively frequently. And we've also seen an optimization of LRU with the second chance algorithm. So here we have clock and reference bits, and actually every page gets a second chance before it's kicked out. So this algorithm is actually used in some of the operating systems today because it's a bit more useful than LRU here. Now, one problem we've seen is what we call thrashing. So when our paging out strategy is actually not good, then it might happen that we just paged out a page and our page fault after that would just request that page again. So access the page again, and we'd have to page it in again. So what's the problem with paging in and paging out? Now, the problem is that an external storage medium is several orders of magnitude slower than RAM. So whenever we imagine a DRAM cell would have an access time of maybe 10 nanoseconds, if we're lucky, if it's in the cache, or maybe 100 nanoseconds if it's in RAM. An access to hard disk, for example, would be in the order of several dozens or hundreds of milliseconds. So this is 1,000 times slower. And even fast SSDs don't make it that much better. So a fast SSD or an SSD has the advantage, it doesn't have these seek delays because it doesn't have to physically move heads around the disk to find the right track. But still, an SSD has limited throughput. So the fastest SSDs on the market today, you can afford to have a throughput of about, I think the one in this MacBook here has around 5 gigabytes per second, whereas main memory throughput is in the order of 100 gigabytes per second. So there's still a factor of 20 in between. So thrashing is something we want to avoid because thrashing, due to these large differences in access speed between external storage and main memory, means that when thrashing occurs, then the related process spends more time waiting for the operating system to handle page faults than being executed. Well, That's something we want to avoid, and we've seen two solutions for this. The first one is we can try to swap whole processes. So we can figure out, is there an inactive process, like a background process somewhere? Those do not require page frames right away because they're not running anyways. So we can temporarily swap the whole process out to disk. And the second solution is based on a so-called working set model. This is using this 80-20 rule I mentioned before. So 80% of the code uses only a small fraction, 20% of memory pages. This 80-20 rule can be found in very many systems. So it's nice to see. It's an approximate rule, obviously. It's nice to see it applies here too. So what we need to do is we need to approximate the set of pages that's really needed by a process. And that's what we call the working set. And we see the WS clock algorithm to implement this approximation of the pages that are needed by a process. Now, that was a very quick overview of virtual memory. It's an important technology, and I didn't explain all the algorithms in detail again. So for the theoretical exercise 4, and obviously for the exam later on, it's very important that you go through the exercises, really try to figure out, to understand how the algorithms work, what their advantages, disadvantages are. So we've given you a number of exercises here for memory management and virtual memory, because it is the basis for all modern computers. It's the basis for providing flexibility and also the basis for providing protections. And we've seen that different approaches, different algorithms can have significant impact on the performance of a computer system. So if we have thrashing, we spend most of the time just copying blocks out to disk and back from disk to main memory again, instead of doing useful calculations, for example. And what something we'll see later on when we talk about cloud computing and virtualization is that there are also ways to have a multi-level mapping of virtual memory. So we have several levels of virtual addresses. And this is actually the basis to provide virtualization. So for example, to enable you to run several different operating systems at the same time on one computer using a hypervisor or VMM, virtual machine manager, like VMware, for example, or VirtualBox. So that was the contents of today. And of course, some of you at least have noticed we have a forum finally. Oh my goodness, that has taken far too long. So this Discord server is running nicely since last Tuesday. And it seems none of you have tried to hack it, or none of you have managed to hack it so far. Thank you. So ED has provided us with a VM. If we figure out it's not really fast enough, we can get more resources thanks to virtualization and virtual memory, obviously. And you can access it using this probably, easy to remember URL. So it's just the course number TDT4186.ed.ntnu.no. And Espen has sent an invitation email to all of you. I received 2 or 3 emails that people have not received an invitation email. So if you have not received an invitation email and want to participate in the forums, let us know. So currently, like yesterday, there were only about 100 users registered, but there's about 420 on Blackboard. So I don't know if you just decided one of your group is enough to register there. That's perfectly fine. So you feel welcome to register on the forum, to ask questions about topics, about exercises, about lecture contents. And the TAs and I look into the forum regularly and try to answer things. And of course, you can help each other there. That's very welcome. And if you're interested in general operating systems topics, like some stuff mentioned, for example, in previous Q&A sessions, I'll also post some links from time to time. So you get some additional information, which is not relevant for the exam or the course in itself, but if you're interested in operating systems. So that's all from me for today already. I think most of the questions have been answered in the forum. So if you don't think there's a question we should discuss here, then that's all from my side. Otherwise, please go ahead and type a question in the chat. When will Practical 2 be released? Yes, I think you already sent me an email about if it would be possible to have practical 2 earlier, since we extended the deadline. So the idea was to release practical 2 next Monday, so after the submission deadline for the first practical. We could release it earlier, but I'm not sure if that would put too much pressure on your fellow students. Like if they see, oh my goodness, practical 2 is already out, we have to start on this. Of course, we will give you 3 weeks for practical 2, so we'll just move all of this back 1 week. And for practical 2, this is about synchronization and p-threads, so you'll also get a p-threads tutorial. Another question, is it possible to purposefully mmap pages that will trap if you try to access them and then catch those traps? Like mmapping 16 pages of read-write followed by 1 sentinel trap page. Yes, you can do this. So you can use, I think it's a system call called mprotect or madvice, depending on the operating system. I need to Google this, to be honest, because that's nothing I'm using all day. So it's mprotect from the Linux man page. So you can use mmap for something, and then you can use mprotect, like in this man page here. That's the first one I found on Google, to be honest, to set this pkey protections on the region of memory. And if you look at the man page, you can set a protection of prot none, and this would generate a page fault. Now the question is, what can you do with a page fault? Because this kicks you into the operating system, right? And you usually can't control the operating system. But what you can do is, we haven't talked about Unix signals so far. We're going to talk about them in a bit. But when a page fault occurs, so a segmentation violation in Unix terms occurs, then you are delivered a signal. So you can register something called a signal handler, which is something like a callback function that can be called from the operating system inside your application. And then you can actually change the protections or whatever you want to do with this empty page. So you could do something like this, but of course there's quite a bit of overhead, because this page fault involves going to the operating system, creating or erasing a signal, and then you handling the signal. So it's a bit expensive, but yes, this can be done. And something like this is done by the operating system, for example. So very often the page between the heap and the stack, or a range of pages, is mapped as inaccessible. So when either the heap threatens to overflow, so the heap starts from low addresses and grows to higher addresses, whereas the stack grows from the other side. So if you have large amount of data on the stack or on the heap, so on the stack because you do like a recursion of 10 million recursive calls, or on the heap because you do large memory allocations with malloc. So there's a protection page to avoid the heap running into the stack with allocations. Now, unfortunately, this is not a perfect protection. So it has been shown that this can be exploited by some security conscious hackers who try to exploit your system by creating a stack overflow to overwrite your heap. So stuff like this is still possible, but that would be part of a security course, maybe an OS security course. Yeah. Right. So I guess there's no more questions for now. And of course, you're always welcome to ask a question in the forums. And yeah, if there's nothing else, the new theoretical exercise videos and slides for this week are online. I'll put this video here online here, and Espen will take questions related to the practical exercise right now, I guess. Yes. Or yeah. Espen, will you also be available at 2 o'clock, or just in case? Or yes, okay. So I tune out for today because I have a set of other appointments. So I'll make Espen the host and I'll stop recording now.